Howdy folks, so I want to run through how do we prove that a limit is infinity using something like our epsilon delta definition. So you guys have been working a number of these problems where you've been finding limits, and you've been doing it for linear functions or in some cases a quadratic function or something. Now we want to look at proving that the limit is infinity, and this is something that we did back in section 2.4. We said what it meant for the limit to be infinity as x approaches some finite number, in this case a. So we said that basically it means that the y values become arbitrarily large, and we want to do a little bit better job of cleaning up what we mean when we say that. So this is a brand new definition. This is different than our epsilon delta definition, which is how we prove that the y values of f approach a fixed point. When we want to prove that the y values become arbitrarily large, we need to give a different definition. So we can think of m here as a large number. So given some large number, can you find a delta so that as long as your x values are within delta of where the limit's supposed to be? Again, this is just how we define closer to a. As the x values get closer to a, what happens? The y values of this function become arbitrarily large. And if that's the case, then we're going to say that the limit is equal to infinity. So let's go ahead and take a look at using this, and we're going to do it with this proof right here. We're going to prove that the limit as x approaches 0 of 9 over x squared is infinity. That means the closer x gets to 0, the larger y becomes. So let's just say that. The closer x gets to 0, the larger y becomes. Okay. So before we do that, I need to make use of one quick fact right here that you saw in an algebra class, but I bet you're a little rusty on it. So if we take an expression like, say, 2 is less than 3, and by the way, this so we've got 2 is less than 3 here. What do we say about the reciprocal of 2, which is 1/2, and what do we say about the reciprocal of 3, which is 1/3? How are these two fractions related? Well, 1/2 is greater than 1/3. So if a is less than b, then 1 over a is greater than 1 over b. And let me just add, just so we don't get into trouble here, if these numbers are both positive, so they can't be 0. Okay. So if I take the reciprocal of an inequality on both sides, I need to go ahead and switch the direction of that inequality, is essentially what we're saying here. So we're going to use that fact going forward. Okay. So let's go ahead and do the scratch work for this problem, and this is going to look a little bit different than our epsilon delta proofs. One, you'll notice in the definition there was no epsilon. Okay? So we already have a guess at the limit. Our guess is that the limit as x approaches 0 of 9 over x squared is infinity, and so now we do the scratch work to find a formula for delta. That part hasn't changed. Formula for delta. That part hasn't changed, but the difference is we don't have any epsilon in this proof. Instead, what we have is we've got some m. And m we can think of as a large number. So we're going to assume that we can make 9 over x squared greater than m for some number m, and we're going to look at what the consequences of that are. So the first thing I'd like to do is let's go ahead and multiply both sides by x squared, so that gives us 9 is equal to mx squared, or 9 over m is greater than x squared. Okay. One thing that I'll just say real quickly, it's important that all of these quantities are positive, and sure enough, x squared is a positive quantity, and 9 over m, that's positive. Okay, so what I can go ahead and say then is that the absolute value of x then, let me keep everything on the same side, that the square root of 9 over m is greater than the absolute value of x. Okay, so essentially one way of looking at that is I applied the square root property, but it's a little bit different when you're working with inequalities. So I don't want to get into that too much, other than to say that it was important to note that 9 and m were both positive quantities, and then I went ahead and ensured what we had here on the right hand side is a positive quantity as well by putting that absolute value in there. So this simplifies to be 3 over the square root of m needs to be greater than the absolute value of x. And my last little step is to say 3 over the square root of m needs to be greater than the absolute value of x minus 0. And this right here is going to be the formula for delta in the proof. So now we're ready to do the formal proof. And let's go ahead and say let m greater than 0 be given. So this is different than our epsilon delta proofs, where we're given a very tiny quantity for epsilon. Instead, what is done is we're given a very large quantity for m. Okay? So then what we're going to do is we're going to say, let's set delta equal to 3 over the square root of m, so that and this part should look a little bit familiar, whenever 0 is less than the absolute value of x minus 0 is less than delta, we have. And now let's go ahead and look at f of x. Well, f of x is 9 over x squared. And let's be a little bit careful here. We know that x, so we know that x is less than, absolute value of x anyway, is less than 3 over the square root of m. And so then if I were, notice here I'm dividing by x squared. Okay? And so because I'm dividing by that, think of that reciprocal property that we talked about. We're going to say that that is greater than 9 over 3 divided by the square root of m quantity squared. And now all we need to do is sort of follow through with the algebra. We've got 9 over m in a fraction, and if we divide there, we get 9 times multiplying by the reciprocal, m over 9, and we get m. So what have we just shown? We've shown, so we're done with the proof there, but let me just reiterate. We've just shown that f of x can be what? Made greater than m. And there's a quick little proof to show that the limit actually comes out to be infinity. So I'm going to let you guys try that in number 26 here. Let me know if you have any questions.